All right, let's jump right in. We're about to go on a journey, connecting the invisible, frantic dance of atoms to the massive forces that literally shape our weather, our climate, and life itself. It all starts with really getting the difference between feeling hot and the energy that actually makes things hot.
Okay, picture this. You've definitely been here. You're at the beach, it's a super hot day. The sand is scorching, like you have to do that frantic hop dance to the water. But the water itself? It's perfectly cool, almost cold. Now think about it. They're both under the exact same sun, getting hit with the exact same energy. So what gives? The answer is hiding in plain sight, in the unique way sand and water handle heat, and that's exactly what we're going to unpack.
So here's how we'll break it down. First, we'll look at the microscopic dance. Then we'll figure out a material's secret property, its fingerprint. After that, we'll actually put some numbers to it. And finally, we'll see how this one little concept pretty much runs our entire world. Let's do it.
To solve our beach mystery, we have got to get our terms straight. You know, we throw the words heat and temperature around all the time as if they're the same thing, but in physics, they're not. They're related, for sure, but they're two very different ideas. And it all starts with atoms and molecules just constantly moving around.
Okay, so here's the deal. Heat is the total amount of energy from all of that molecular motion in an object. Think of it like the entire energy budget of the substance. Temperature, on the other hand, is just the average energy. It's a measure of how fast, on average, those molecules are jiggling around. That's why a giant iceberg, a massive one, technically has way more total heat energy than a hot cup of coffee, even though its temperature is way, way lower.
And this shows you exactly how they're connected. When you add heat to something, like you're boiling a pot of water, you're literally just pumping energy into it. That energy makes the water molecules go crazy, they start vibrating and moving around way more intensely. And that increase in their average jiggle speed is exactly what we read on a thermometer as a rise in temperature.
We measure this average energy using scales, usually Celsius or Kelvin. Celsius is the one we all know, based on water, but Kelvin is the absolute scale. 0 Kelvin means everything stops, all molecular motion just ceases. The conversion is super simple though. Kelvin is just your Celsius temperature plus 273.
All right, so back to the beach. If the sun is dumping the same amount of heat energy onto the sand and the sea, why does the sand's temperature go through the roof while the water's temperature barely even moves? Well, the answer lies in a kind of hidden property that acts like a unique fingerprint for every single material out there. It's called specific heat.
So here's the official definition. Specific heat capacity is just the amount of energy, in joules, you have to put into 1 kilogram of a substance just to raise its temperature by 1 single degree. So let me put it another way. A substance with a high specific heat is really greedy. It needs to absorb a ton of energy before it starts to feel any warmer.
Yeah, a really great way to think about this is thermal inertia. It's like a material's stubbornness. It's just its natural resistance to changing its temperature. And a material with high thermal inertia isn't just hard to heat up, it's also really, really slow to cool back down.
And would you look at these numbers? This table tells the entire story. Look at water. Its specific heat is a whopping 4,200. Now compare that to sand, which is down to just 830. This means water can soak up a ridiculous amount of energy, and its temperature just doesn't change that much. Sand, on the other hand, it takes just a little bit of energy to get screaming hot really fast. And that is the answer to our beach mystery.
Now, this isn't just some vague concept. It's something we can calculate with incredible precision. Physicists have a really straightforward way to figure out exactly how much heat energy you need to change something's temperature. And you know what? It all boils down to one beautiful little formula.
And there it is. Q equals mc delta T. It looks simple, and it is. This little equation ties everything we've just talked about together. Q is the heat, M is the mass, C is that unique specific heat fingerprint, and delta T is just the change in temperature.
Let's just break it down real quick. Q is the heat energy we're trying to find, measured in joules. M is how much stuff you have, the mass in kilograms. C is that special number we saw on the table, the specific heat. And delta T is just the difference between where you end up and where you started. Final temperature minus initial temperature. Easy. So let's run a quick calculation just to see it work. Let's say we have a little piece of copper, about 0.3 kilograms, and we want to heat it up from a room temperature of 20 degrees Celsius to a toasty 70 degrees. How much energy is that going to take?
Well, to get the answer, you just plug in the numbers. We multiply the mass, that's 0.3 kilograms, by copper-specific heat from our table, which is 390, and then by the temperature change, which is 50 degrees. And what do you get? 5,850 joules of energy. It's a perfect, simple example of this physics in action.
Okay, so we've seen the science, we've done the math, but this is where it gets truly mind-blowing. This one property, specific heat, doesn't just explain why your feet get burned on the sand, it explains massive, planetary-scale phenomena that literally make our world a place we can live.
A perfect example of this is the sea breeze. You know that cool, refreshing wind you feel at the beach in the afternoon? Well, that daily weather pattern is driven entirely by the different specific heats of the land and the water.
So here's how it works. During the day, the land, with its low specific heat, heats up way faster than the water. This hot land heats the air right above it, making that air less dense, so it rises. Nature doesn't like a vacuum, so to fill that gap, the cooler, denser air sitting over the ocean rushes in to take its place, and boom, that's your sea breeze. Then at night, the whole thing reverses, because the land cools down faster.
Now, let's scale that idea up from one beach to the entire planet. Our oceans act as these absolutely colossal heat sinks. They soak up enormous amounts of energy from the sun all day and all summer, and then they release that heat back out very, very slowly at night and during the winter. This process prevents wild temperature swings and keeps our entire planet's climate stable.
And that climate stability, it is absolutely essential for life. The stable temperature of the oceans is what allows cold-blooded animals, or poikilotherms, to survive, since their body temperature just matches their environment. But it also creates the stable world that warm-blooded animals, homotherms like us, need to exist in the first place.
And really, this brings us to one of the most fundamental truths about our planet. Without water's incredibly high specific heat, without its amazing, stubborn resistance to changing temperature, life as we know it, well, it just wouldn't be possible.
So, this is the big takeaway. This is where our journey ends. We started with the invisible jitters of single molecules, and we ended up seeing how that one simple property, specific heat, when applied across our vast oceans, is powerful enough to define our global climate and make all of life possible. So I'll leave you with this final thought. Just for a second, imagine a world where water had the same low specific heat as sand. A world where the oceans could heat up and cool down in just a few hours. What would our daily temperatures be like? Could our climate even exist? It's a question that really makes you appreciate just how finely tuned and how truly remarkable the physics of our world really are.